In this video, I will address some properties of the limit of a function at a certain point. So I will first list out these properties that you may need to know for the IB syllabus, and afterwards I will give proofs for some of these properties, and the rest of the properties that I won't prove, well, perhaps I'll leave them as exercises for the viewer. Okay, so first of all, if the limit of a function at a point A, let's say of f, and we'll write f instead of f of x, is equal to some value L, and also the limit as x approaches A of another function g is equal to m at A, then the limit as x approaches A of the sum or difference of these functions is equal to the sum or differences of the limit, respectively. So if we're taking the sum of the functions, then the limit as x approaches A of the sum of the functions is equal to the sum of the limits. And if we're taking the difference of the functions, then it's equal to the difference of the limits. Okay. 2. If the limit as x approaches A of f is equal to L, then the limit as x approaches A of c times f is equal to c times L, where c is any real number. Okay, so that's straightforward. 3. If the limit as x approaches A of f is equal to L, and the limit as x approaches A of g is equal to L, then the limit as x approaches A of f multiplied by g is equal to L multiplied by m. 4. If, again, the limit as x approaches A of f is equal to L, and the limit as x approaches A of g is equal to L, sorry, not L, m, and m is not equal to 0, then the limit as x approaches A of f divided by g is equal to L divided by m. Okay, so really these are pretty much all the properties that you're going to be using. There are a couple of more properties which involve continuous functions, but I think I'll go over them in a different video. So for now we'll address these properties, and from now on I'll be stating the proofs of these properties. So if you're not interested in the proofs, then you can stop the video here. Okay, so for property number 1, which involves the sum or difference of limits, I'll just do the case for the sum of limits. The case for the difference of limits I'll leave to the viewer, as it's quite similar. Okay, so again, going as per definition of the limit of a function as a point, which I discussed in the previous video. By hypothesis, we know that the limit as x approaches A of f is equal to L, which means that for all epsilon greater than 0, we can find an interval of width 2 delta around A. So such that as long as we pick an x within that interval, the distance between f of x and L can be made less than epsilon. And the analogous situation for g, except instead of L we have m. Okay. So, therefore, suppose let's pick some arbitrary value. Let's call it I don't know, let's call it epsilon O. Okay, and let's say we want f of x to be a distance away from L less than epsilon O over 2. Okay, so as per the definition of the limit at a point, we know that there exists some delta 1 greater than 0, so that if x minus a, if the distance between x and a is greater than 0 and less than delta 1, then this, highlighted in red, underlined in red, is true. And we can also find an interval around a, perhaps of width 2 delta 2, such that if the distance between x and a is less than delta 2 and greater than 0, then g of x minus m, the distance between g of x and m, can be made less than epsilon 0 over 2. And this is true for all x distance less than delta 2 away from a. So these are just two statements which are true as per the definitions of the limit of a function at a point. Now, we have to discuss an important result, and it's called the triangle inequality. Okay, triangle inequality. And it's actually quite a simple inequality. It can be stated in one line. And it says that a plus b is less than or equal to the absolute value of a plus the absolute value of b. So the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b, where a and b are both real numbers. So this is a fact, and it can be proven. There are a number of different ways to prove it. Perhaps the nicest way actually just involves a triangle. So you can sort of try constructing a triangle yourself and exploring why this is called the triangle inequality. It's actually closely related to the cosine rule, and its proof is not too difficult if you invoke the cosine rule. But we will take that as a fact for now. So let's take a look at f of x minus L into brackets plus g of x minus m. Well, the absolute value of all of this by the triangle inequality, which we've previously stated, is less than or equal to the absolute value of f of x minus L plus the absolute value of g of x minus m. Now, as given, we can ensure that x is a distance less than delta 1 away from a, then we can ensure that this right here is less than or equal to epsilon 0 over 2, as per this over here. And if we can ensure that x is a distance less than delta 2 away from a, then we can ensure that this right here is less than or equal to epsilon 0 over 2 by this line over here. So how do we ensure that x is a distance less than delta 1 away from a, and x is a distance less than delta 2 away from a? Well, it's actually quite simple. All we have to do is ensure that x is less than the minimum of delta 1 and delta 2. So whatever the minimum of delta 1 and delta 2 is, if we ensure that the distance between x minus a, the distance between x and a is less than this minimum value and greater than 0, then both these statements here must be true. So why is that the case? Well, let's take a look at a number line over here, and let's suppose that this is a, and this is an interval width 2 delta 1, and perhaps this is a larger interval. Perhaps delta 2 is a bigger number, so of width 2 delta 2. Now if we want x to be both within both intervals, then all we require is that x is within the smaller interval, whatever the smaller interval may be. And the way we do that is we just make sure the distance between x and a is less than whatever the minimum of delta 1 and delta 2 is. So if delta 1 is 3 and delta 2 is 4, then the minimum of 3 and 4 is simply 3. As long as we ensure that x is within the smaller interval, then it's obviously also within the larger interval. So, given the distance between x and a is less than the minimum of delta 1 and delta 2, we can ensure that both of these statements are true. So we can ensure that the distance between f of x and L is less than epsilon 0 over 2, and we can ensure that the distance between g of x and m is also less than epsilon 0 over 2, which means that the sum of both of these, so the sum of the distance between f of x minus L and g of x minus m, is less than or equal to epsilon 0 over 2 plus epsilon 0 over 2, which is just epsilon 0. So this is given that x minus a is less than the minimum of delta 1 and delta 2 and is larger than 0. But remember, epsilon 0, we didn't specify what epsilon 0 was. Epsilon 0 was just an arbitrary value larger than 0. And given an arbitrary value larger than 0, we were able to find a number. So we can let's call the minimum of delta 1 and delta 2 delta 3. So let's say delta 3 is the minimum of delta 1 and delta 2. So we were definitely able to find a number. The number is the minimum of delta 1 and delta 2. So that as long as the distance between x and a is less than the minimum of delta 1 and delta 2 and larger than 0, the distance between f of x plus g of x and L plus m can be made less than epsilon 0. Now why is that? Because the stuff here, so f of x minus L plus g of x minus m, is really the same thing as f of x plus g of x. So if we view the sum of two functions as one function, minus L plus m. So the absolute value of that. Now as per the definition of the limit of a function at a point, given we can make this as small as we like, which we've just proved we can because epsilon 0 is an arbitrary value, the limit of this function, so the actual sum of f of x and g of x, is in fact whatever this number is, which is just the sum of the limits of these individual functions, so L plus m. Alright, so that's a proof of the first result. Now, it turns out that the second result, namely this one, is pretty similar in its proof. So this you guys can try for yourself. And these ones are a lot more challenging. So proving that given this is true, that the limit of the product of the functions is equal to L plus m. This is a lot harder, but I will also leave it. And of course, and the quotient 1, which I stated in the first part of the video, to prove that is also a lot harder. So maybe I'll leave the proofs of those results to separate videos of their own, because there's certainly not enough time in this video to discuss these results. And of course, you can try to prove these results for yourself. Thank you.